By many measures, SQL injection is the #1 risk on the web today. It's very easy to discover the risk, it's very easy to exploit it, and I'm going to show you just how easy in just a moment. And the impact of an exploit is significant. We are talking about exfiltrating data from a system, modifying data in the system, and possibly even pivoting through into internal networks and doing a lot of damage even beyond the firewall. So it's an extremely serious risk, and it's a good place for us to start. Let's jump in, and I'll start by giving you a walkthrough of the mechanics of a SQL injection attack. Let's talk about how this attack actually works. Now imagine we've got an attacker who's going to be communicating with a web server which sits in front of a database. Now the attacker is talking to the web server simply by making web requests. They could be over HTTP or over HTTPS. It doesn't matter. The point is that the attacker is able to send requests to that web server. Now very often, when a web server receives a request, it prepares a query and sends it off to the database. And that query is often constructed from data that the user provides to the web server. Now under normal operating circumstances, that data is entirely innocuous. The user might be asking for a certain record, for example. In a SQL injection attack, the attacker is going to malform that request in order to change the execution path of the query. So they're actually going to get the query to do something that it was never intended to do. Now when that query runs, the database responds back to the web server with a result. Now usually the result would be a record set. Certainly that's one of the more common outcomes of running a query against a database. But the result could also be an internal exception on the database. So what will often happen in a SQL injection attack is the attacker is trying to cause an error in the database such that the error is then returned to the web server and then eventually to the attacker. Now this is a particular style of SQL injection attack that we call error-based SQL injection. So one which is dependent on the attacker causing these errors and then seeing the errors from the database in the website. This all becomes much easier to visualize when you actually see it in action. So let's jump over to the browser and I'll show you exactly how an error-based SQL injection attack works. This is a sample application I've built for this video, and it's all about snowboards, getting ready for the coming winter season. It's on a fictitious domain, snowboards.com, and this app has got a number of different security risks in it. And in fact, they're the very risks that we're going to be exploiting in order for me to demonstrate how they actually work. Now we're going to start out by looking at the risk of SQL injection. And here's how I'd like to demonstrate this. We'll notice on the front page we have 3 different brand logos down towards the bottom. Now I can choose one of these and drill down into it. I'm going to take a look at the Burton boards, so we'll choose Burton. And here we see 4 different boards. Inevitably, if I choose one of the other brands from the previous page, I would see different boards. This is very typical web behavior. And the way it's implemented is by passing the brand ID in the URL. So you can see up there in the address bar, brand ID equals 1. And inevitably 1 is Burton. Now what often happens in an online system like this is that brand ID from the query string would go into a query against the database and a result set would return with all the Burton boards. So that piece of data often ends up in a SQL query. Now what an attacker wants to do in a SQL injection attack is start to modify this data such that the query does different things. Things that it was never designed to do. Let me show you what I mean. I'm going to jump up to the address bar, and what I'd like to do here is just change that 1. And I'm going to change it to a 1x. Now what's significant about doing this is that it's now no longer going to be a number. Let's see what happens when we load this URL. So this is where the SQL injection attack begins. We've got ourselves an internal exception here that's bubbling up and appearing in the web application. Now we can see a title here, incorrect syntax near X. And just beneath that, we can see some exception details that explain that it is a SQL exception. Now this means it is actually an exception in the database, which is bubbled up, so it's been returned from the database to the web app and eventually appeared in the browser. In an error-based SQL injection attack, the attacker wants to exploit this error reporting. Let me show you what I mean by that. If we were to replace the value of this brand ID and start changing it to other values, so for example, we might change this to a subquery and we'll make it something like select star from users. Now when we run this, we get a different error. Invalid object name users. This is actually the database saying that there is no table called users. And because the web application is improperly configured, which is a very common scenario, and it's returning those internal exceptions, we can actually see that database message. Now, if we keep tweaking this query string value, we can start to get the database to disclose even more information. So for example, let's change users to customer. We get a different type of exception now. And in fact, what this exception is telling us is that this particular subquery, and this is what it is because there's another query wrapped around this that's looking for a value returned from what we're just passing here in the URL. But this particular one here is returning multiple results, and that's not something that the query in this application can handle. Now that doesn't matter so much because the important thing is that we've been able to cause an error such that the database has told us what's going on inside it. Let's try probing away a little bit more. I'm going to change the select star in the URL here to select top one password. Now you may also notice every time I enter a space, after I load the page, it replaces it with a %20. That's just URL encoding that the browser automatically adds. It still means that the web server sees a space sent in the request. Let's try this one. And now we actually see a really interesting error. And in fact, the error we see here has a password in it. It's this one right here, encapsulated in quotes, password with a 0. And this is a legitimate password from the customer table in the database. And the reason that we're seeing it in the error message here is because the query has actually tried to check for a brand ID that is equal to the word password with a 0. Now that brand ID in the database is normally a number. And when the database is asked to compare it to a string, an exception has occurred and been returned in the response. And that's what we see right here. So we've actually managed to find a password in the database simply by changing the URL in the web app. Now attackers use this mechanism to exfiltrate huge amounts of data out of systems. It might look a little bit laborious doing it like this, but it can actually be highly automated. In fact, I want to show you just how much we can automate this attack. And to do that, I'm going to go and grab a little piece of software that's going to make this very, very easy. What we're looking at here is a tool called Havage. It's freely available on the internet and it makes SQL injection an absolute breeze. Here's how it works. I'm going to select everything that's currently in that target field, and I'm going to paste in the URL that we were just on, the legitimate URL, the one that showed the Burton snowboards. I'm now going to jump up and hit Analyze just next to that target. And down the bottom, we see that it goes away and makes a few requests to the website. Now, what we can do after that initial analysis is start asking Havage to get us more data out of the database. In fact, what I'd like it to do is go and have a look at the tables in the database. So I've hit the tables button. I'm now going to say get tables. And here we go. There are 4 tables in the database. Now I'm really interested in this customer table because it sounds like the sort of information that an attacker would like. So I've checked that. Let's now go and get the columns of that table. And here are our columns. This is pretty useful information. Now I, as an attacker, would like to get the email address, the name, and the password out of that database. Those 3 fields will do. Let's now go and get the data. And here we go. It is just flying through those records. And Havage is doing exactly what we just did in the browser. It's issuing requests to the website, which are formed specifically to get the database to throw an exception and then return that exception to the website, and the website being misconfigured and showing those internal exceptions actually leaks the internal data of the system. This will just keep going and going and going until it gets all the data out of the system. And this is how easy SQL injection can be. Find a potentially vulnerable URL, so typically one with a query string, copy it, paste it into an automated tool, and that is often all that is required. So that's how easy SQL injection can be. Let's now go and talk about how to defend against the risk. There are a few really fundamental practices that are used to defend against the risk of a SQL injection attack. And the first one is simply validating untrusted data. So what I mean by untrusted data is anything that comes from an external party. So when we changed the URL, that came from us as an external party. And the question that the application has to ask is this valid data? So in the case just then, the application should have been expecting a brand ID, which was a number. It should not have been accepting something that wasn't a number. That was never going to be valid data, but the app allowed it anyway. So that was the first point of failure. The next one, and this is really the heart of defending against SQL injection risks, is parameterizing queries. Now what this means is writing the query using parameters that keep the query itself and the untrusted data entirely separate. No matter what data you actually pass to the database in the query, it never changes the execution of the way the query was originally designed. So this one here is absolutely critical. Another one that's frequently overlooked is locking down the database. So let's say an attacker does manage to find a SQL injection risk in the application. Because the attack is predicated on the app talking to the database, the scope of damage that the attacker can do is entirely limited to what the account the web application is using can actually do in the database. So for example, should the web application actually be able to read every single column of every single table? Usually not. Or let's take it a step further. Should the application be able to run commands that are normally reserved for system administrators on the database? Almost certainly not. And this talks to just how far an attacker can go with SQL injection. At the absolute upper end of the scale of impact, an attacker can run system commands on the database. Now, once they can do that, they can start pivoting through the internal network as well. So this is not just about an externally facing risk. And certainly there are many documented examples of the attacker being able to run arbitrary commands on the database server that give them access to a whole raft of internal machines well and truly firewalled off from the publicly facing domain. And this is often the case with SQL injection as well. The database server sits behind a firewall, only the web application is allowed to talk to it, but if the web application is issuing malicious commands, even though that database may be sitting there within a private network, the attacker now has control of it. Now, in addition to these three things, there is the whole defense in-depth approach. So applying layer upon layer of security defense. Something like a web application firewall, for example, is an additional defense that would block many SQL injection attacks. Even good cryptographic storage of the content stored in the database would put a big dent in the impact of an attack if an attacker got the data out and couldn't actually use it. Defense in depth is a concept that we're going to keep coming back to throughout the remainder of this video because it really is a fundamentally important practice. Don't just leave one point of failure. This is about putting multiple locks in place so that even if an attacker manages to break through one, maybe even two different layers, there's still another wall of defense. So that's SQL injection. Next up, we're going to take a look at insufficient transport layer security.